All right, folks, we just finished off page number 1 of the notes on slope fields, and I want to give you a little commentary here on connections between what I've asked you to do in the notes and what you might see on the AP exam. So when I asked you to graph the slope field, I gave you 25 points. I gave you a 5 by 5 grid there. So 25 different little slope segments we had to put on that graph. You won't be asked to do that many on the AP exam. So let's just quickly talk about the AP exam real quick. As you recall, I divide up free response questions into buckets. We now have this bucket of problems we can do, the differential equation problem. So what do those typically look like on the AP exam? I just want to show you one or two here real quick so you can get an idea of how slope fields might show up. Here in 2016, question number 4, you're given a differential equation. You had to sketch the slope field for 6 points, not 25 like we did in the notes. In 2015, there was a similar question where you had to sketch the slope field for 6 points, not 25. The reason why I asked you to do so many in the notes was just to get some practice. Okay, let's now jump back here and start with page 2. Next thing I want to talk about with respect to slope fields is how to read a slope field. And that's to determine what is the slope field telling you about the particular solutions at a specific point, and can you match it back to an actual differential equation. So I got 4 kind of bullet points here to look for. The first one is, where are the slopes 0? That is, where does dy dx equal 0? And we know that if we have a rate of change equal to 0, we have a horizontal line. Second thing, what are the slopes along the x-axis? That's when y equals 0. And what are the slopes along the y-axis when x equals 0? Why do I highlight these? Those values can be very revealing about which differential equation you're looking for if you're trying to match a slope field to a differential equation. Next, do the slopes only depend on x, or do the slopes only depend on y? And as I look at the examples I gave you here, take a look down here. You'll notice that those differential equations are all either constants or have only an x in them. So I'm going to kind of show you an additional thing here of what I mean about, do the slopes only depend on x or do they only depend on y? So I'm going to switch to a different view here. Let's take a look at these 2 slope fields. And I have a horizontal line and a vertical line that I'd like to kind of drag across each graph and show you what I mean by this. So let's take a look at this vertical line. When I put that across this first slope field, I see that all of the slope segments along that vertical line are the same. So that means as y changes, because as we follow this vertical line up and down, y is changing. But as y changes, the slope field does not. So this is a graph that does not depend on y. So there will be no y variable in that differential equation. But let's look at what happens when we drag a horizontal line across there. Okay, so as x is changing, and that's what happens when you move along a horizontal, as x changes, you definitely see that those slope segments are changing. So that differential equation, that slope field, is going to be for a differential equation that definitely has an x in it. So I know that this one has an x in it, but no y. In fact, this one is for y prime equals 2 minus x. So that's just to indicate what a slope field will look like if it depends only on x. You will see no change as you scan up and down vertical columns, but you will see a change as you scan left to right horizontally. Okay, now let's look at the second graph. So I'm going to go ahead and move my my vertical segment here across onto the graph, and you'll take a look. As I scan up and down this vertical line, I see the slope segments are definitely changing. So that differential equation is going to have a y in it. Now let's look here as we scan left to right. No change. So this guy here does not depend on x. In fact, this differential equation is y prime equals 1/2 times the cube root of y. And again, I'm just trying to provide you examples here of things you can look at to see, all right, what the slope field, what is the actual differential equation going to look like based on what you see in the slope field. Okay, now back to the notes. Fourth pointer I have here for reading a slope field is to look where are the slopes positive and where are they negative, because again, that can be an indication of what the original differential equation looks like. So let's go ahead and start here. Question 3 says match each slope field with the equation that the slope field could represent. So when I go ahead and look here, I've got 6 different differential equations. I got 6 different slope fields. What I'd like to do is kind of look at these in terms of what I consider to be easy. I'll do the easy ones in green, medium, I'll do the medium ones in blue, and then challenging, I'll do the harder ones in red. So we'll start with green. Let's take a look at this differential equation right here. dy dx equals 0. Do we have any slope field where we see all of the slope lines are horizontal? I sure do. It's this one right here. So this is this graph corresponds to differential equation number 1, which is dy dx equals 0. Let's take a look at another constant. I got dy dx equals 1. Do you see any slope field where all of the slope segments have a slope of 1? Sure enough, I see that here. So this one is dy dx. So we've taken care of the easy ones. Now let's take a look at a couple medium ones. What I'd like to do for these 2 medium ones is actually compare 2 of the slope fields that look similar. So when I take a look at these 2 graphs, to me they look similar. Now let's talk about why they look similar. Well, I see that for negative x values, the slope segments are negative. And for positive x values, the slope segments are positive. And I also see that it flattens out around x equals 0. I have 2 possible differential equations that could match that. And that's these 2 right here. So I have dy dx equals x and dy dx equals 1/4 times x cubed. Both of those differential equations will preserve the sign of the input. So if the input is negative, dy dx will be negative. If the input is positive, dy dx will be positive. If the input is 0, dy dx will be 0. But now let's talk about why this one is number 4 and why this one is number 5. To compare these 2, you almost have to analyze what goes on between -1 and +1 and then outside those 2 values. So let's take a look right in here and just kind of highlight what's going on there between positive and -1. So the graph on the lower right there for 1/4 x cubed, the slope field is almost flat there. And think about plugging a test point in. Think about plugging a small x value in there between -1 and +1. When you cube that, some decimal less than 1, it's going to get even smaller, and then you multiply it by 1/4, it gets even smaller or even closer to 0. That won't be the case with the graph up here with dy dx equals x. Now, that's not what happens once you move out beyond x equals 1. Once you move out beyond x equals 1, the steepness of 1/4 x cubed grows faster than it does for x. Okay, that's enough for the medium one. Now let's take a look at the 2 ones that I think are pretty challenging here, and that's dy dx equals x squared and dy dx equals 1/x squared. A couple things. I mean, obviously we only have 2 graphs left. We got this guy and this guy, so we could coin flip and figure out which one is which. But here's here's some observations I want to make. First of all, for both of these, for this one and for this one, because we have an x squared in there, y prime is always greater than. Now for this one here, y prime will equal 0 at x equals 0. And remember how I said one of my suggestions was to look at what slopes along the y-axis do when x equals 0. Here's why. Because I know that when x equals 0, this differential equation has a slope of 0. But what about here? For x equals 0, y prime is undefined. And when a slope goes towards undefined, the solution gets extremely steep. So what I have to do is pick, for this differential equation right here, I have to pick one that gets really steep as we get close to x equals 0. And that happens right here. So this graph is differential equation number 6, dy dx equals 1 over x squared. And last but not least, this is number 2, dy dx. Okay, that's enough for example number 3. Let's go down to example number 4. Folks, this one's going to be really quick. It says match each slope field with the equation that the slope field could represent. These are all the exact same slope fields as the previous problem. But what is different about this question? Do you have an answer? Well, here's your answer. None of these equations are differential equations. In order to see which of these matches each slope field, we should turn these into differential equations. This one would be y prime equals x squared. Y prime equals 1/4 x cubed. Derivative of constant, y prime equals 0. Y prime equals 1. Y prime equals 1 over x squared. And last but not least, y prime equals x. Okay, seems like it might be a little bit absurd that I asked you to do this, but there is a reason for this. Let's go ahead and take a look back at this slope field right here. And that was the slope field for y prime equals x squared. Well, look at what our particular solution looks like. Our particular solution there would be 1/3 x cubed plus c. And if you pick any point in here and you sketch a solution through that slope field, it's going to look cubic. So what I'm trying to do there is make a connection between differential equations and then the general solution to those differential equations, which is in fact the slope field. Okay, try to go ahead and make that connection between the other graphs, but in the meantime, I want to close this out with some comments. Here's my first comment. Slope fields indicate the slopes given by a differential equation for all x comma y pairs. The sketch through a particular point is a sketch of a particular solution for that differential equation. Second thing I'd like to mention here, the equations in number 4 are not differential equations. They're actually general solutions without the plus c. To see the differential equation, take a derivative. Last but not least, don't forget, particular solutions cannot cross an asymptote of the differential equation. And let's look at an example of what I mean by this. Let's look at number 4, part f, through the point 2 comma negative 1. Okay, number 4, part f, is this graph right here. And that matches up with the differential equation 1 over x squared, which had a general solution of negative 1 over x. Let's graph a point 2 comma negative 1. It's going to be right there. If I were to graph that solution, it would look like that. And make sure you do not pass over an asymptote of the original differential equation. In this case, that is x equals 0. All right, folks, that's it for slope fields. Stay tuned for more fun and engaging work in differential equations.